things that are waves. Waves are periodic. Periodic things go in 2 pi. The 2 pi radians per cycle, things like that. So the 2 pi comes along all the time. And so what is done is the Planck's constant divided by 2 pi is given the symbol h bar, its own special symbol. It's even in Microsoft Word even has it, believe it or not. And so that is just the numbers of Planck's divided by 2 pi. So here's what I want you to do. We're going to imagine all the first column elements, the alkaline metals, going from lithium to sodium, potassium, rubidium, calcium, francium. The N, we're going to presume that we're pulling off all of the electrons except the very last one. Okay, so we have a 1 electron system. Now, here's what I want. You're going to take these 2 expressions right here and simply solve it for the velocity. Okay? Then we're going to take the mass of the electron, you look that up. Z will be the number of protons. It's a unitless number, we'll get to that today. Okay? So you have a Bohr radius, just a constant, you have Z, the number of protons, N will be 1, Planck's constant divided by 2 pi or h bar, mass of the electron, solve for the velocity. Here's what I want you to do. I want you to go down to all the entire column where you start from lithium, which has 3 protons, or 11 for potassium, 19 for potassium, so forth and so on. And I want you to compute the radial velocity, or of the electron. Just take it. I want to be in it.
It out with your hand. Okay, sorry.
But anyway, I want you to compute the velocity, and I want you to calculate what fraction of this is it to the speed of light. Okay? You will be amazed. It's an interesting little example, and we'll explain later why that leads to a stability of the hydrogen atom. All right, now, so that's problem number 3. It's very easy to knock that out in a few minutes. Problem number 4 gets into, we're going to be getting into this. We need some of the mathematics of quantum mechanics. We're going to be dealing with operator algebra, Hermitian functions, things like that. It's not going to be a big deal, but we need to have a little bit of that language to go on. Now, when you talk about finding solutions to waves are frequently complex. That means they involve the square root of -1 over the I. Well, if we're going to start developing the mathematics for representing a wave as matter, so we're going to have a wave that's supposed to represent an electron, or it's supposed to represent like a rotating molecule. So if you have a wave that's representing matter, matter is real, and so how can you have a wave that's complex? Well, we run into this problem frequently when you're talking about waves, which includes sound waves, light waves, things along that line. The solution to that, and very much this is philosophical, is to have the square of the wave. So if you have a sound wave, you square it, and that gives you the intensity of the wave. Okay? So we're going to be doing that in quantum mechanics as well. We're going to come up with a wave that represents an electron in orbit, or whatever it might be, and frequently it'll be complex. Well, how to get a real value out of that is not just to square it. We have to do what is known as a complex conjugate. Here's how it's done. To do that, well, first off, here, for example, let's say I had a function. This is kind of a class. I have a real plus a complex part. And if I square it, so the f squared, I get an a squared, and then I get a 2aib, and then I have an I squared, which is -1 times b squared, so we get the minus b squared. So that's still a complex number, and I can't represent anything real. So what was done is to take what is known as the complex conjugate. Here's all you do. To square a complex number, anywhere you see an I, anywhere you see an I, you change it to a negative I. Okay? Then square it. When you do that, the result will be real. Okay? So in this particular example, I take the complex conjugate, I change the I to a negative I, then I multiply by the value back. So here one has a negative, one has a positive, and when you do that, the cross terms go away, you have a real answer. In the homework problem, this is a little bit more complicated one. I have 3e to the minus 6i, then I've got plus a 2i, And then I've got plus -3 plus 4, oops, I squared. So there's the function. So I want you to square it, okay? So what you do is first find the complex conjugate. So if this is, what did I give it? I call it x. Okay. So x is this. The complex conjugate is going to be 3e to the positive 6i minus 2i, and then plus a -3 minus 4i squared. So just expand that out, square it, and demonstrate that you get something real. Hint, 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 hint. You'll need Euler's relationships. Okay? Where you have e to the ix is cosine x plus I sine x. And if you have this as a plus or minus, that becomes a plus or minus. So you're going to end up with a couple of exponents in there that you can combine into a trigonometric function. Okay? So anyway, this kind of gives you a warm up on doing these sorts of things. Two fairly straightforward problems. Okay? Now, anything else before I launch? We're getting down to it. It's starting to get into the really fun part. First off, I'm going to draw your attention to which I've been hoping you have at least gone to review once in a while, unless you're just intimately familiar with it. This, of course, is the Chemistry OpenStax General Chem textbook. I opened it up to this part because it was a suggested area. This is the part talking about the Bohr model of the atom we're going to look at now. In the Bohr model of the atom, he came up to an energy expression that was a constant multiplied by z squared, the number of protons squared, divided by the quantum number n. N is 1, 2, 3, 4, 5, it's not 0. He said that the radius is n squared over z times what he determined to be the Bohr radius. He said that's the predicted radius of the first electron. He was wrong, but he was right at the same time. Okay? But then this constant here has a value of 2.179 × 10 to the minus 18 joules, and that's the Rydberg constant. So I just want to draw your attention to the general chemistry book, and we're going to reproduce these things. Okay? Now, when we go to the Bohr model, Bohr had no idea about how this thing was working. He did know that when you went into the laboratory for atoms, you get line spectra, not continuous spectra. Now, at that time, this was really an amazing time, in the 1900s and 1930s in that area. At that time, there were a number, we're going to look at before we're done today, a number of different physics experiments to try to explain things that were being utterly failing. It just did not work. When they went through to try to figure out what to do to make it work, a ubiquitous constant seemed to appear all the time. And it's that constant, Planck's constant. And of course, it was originally a fitted constant by Max Planck. Einstein was, at that time, positing that waves have particle behavior. He called them photons. So Einstein, jumping on from this, you see again why in a moment, gave light this quanta of energy, of h nu, Planck's constant times the frequency. When we look at things like solar cells, where you hit cells with light, emits electrons, that comes in a kind of curious multiples of different things, but the H came in that way. Now, Niels Bohr then kind of jumped on that idea, and now turning back to our notes here, he made a couple of then observations. Due to the line spectrum, he deduced that electrons are in fixed orbits. Okay? Now, he says electrons rotate around the nucleus, but they do not radiate energy. That is, the orbit does not collapse. If an electron is going to spiral into the nucleus, and if you calculate that, you'll do that in a femtosecond. If it spirals into the nucleus, it's going to give off radiation. Okay? Well, classical electrodynamic theory said it's going to radiate energy. It's going to decay. Well, it doesn't. So that is in violation of classical theory right there. Then he drew them based on experiments that I'll show you in a moment. He said, okay, the electron is moving at an angular momentum that is in integer multiples of h bar. Again, that 2 pi is because you're going in a full circle, all right? Because we have 2 pi radians per cycle, so the 2 pi pops up. So he has the angular momentum is h over 2 pi. The exception of that, classical mechanics holds. The previous, I'll get to this in the next part about the Debye relationship in just a moment. All right, but I'm going to jump then to when we built in Hamiltonians, which we're going to do. Remember, a Hamiltonian is simply the total energy of the system. It's the kinetic energy plus the potential energy. Well, for my then hydrogen atom model, here's the Hamiltonian. It has then, this is a radial momentum. We'll talk about that in just a second. This is the angular momentum, and we're going to presume that the electrostatic attraction between the two positively charged proton, negatively charged electron is Coulomb's law. Coulomb's law says you have a z, the number of protons, that's the electronic charge, 1.602 times 10 to the minus 19 coulombs, divided by the 4 pi epsilon 0, the permittivity of free space, and inverse distance of the radius between them. All right, going from then the first model, or the first bullet point in Bohr's model, the electrons rotate, but they don't collapse. They're not going in, they're not going out. That means, for the Bohr model, the radial momentum is 0. It's at a fixed radius, okay? Now, here are the 4 equations of motion for 2 dimensions. The only one really we need to worry about is this one, to get to where we need to be, okay? Now, here, this says take the derivative of this Hamiltonian with respect to r, and that will be equal to the acceleration in the radial direction. That's what the p dot is. Remember, anytime you have a dot, that means a time derivative, standard of notation, okay? So this is the radial acceleration, or actually radial velocity. Well, that is, actually it does come out to the acceleration, but that is also, just like this, 0. It's in a fixed orbit. So that kind of gives us where we need to be. So let's get this, it doesn't take long to actually do. So now what I'm going to do is using Hamilton's equations of motion, I'm going to have that the partial of h with respect to r negative is equal to 0, because it's not going anywhere. So then we just take those 2 derivatives. Well, the first term is gone. I have a p theta here now. One other thing. Now I'm going to do the second bullet point, and this angular momentum here, I'm going to set equal to n h bar. Okay? So those are Bohr's principal attacks on doing it. He did not know why. All right. So we do that. So I take this first one. The other one is going to be, I'm going to have a negative n squared h bar squared, that's the p theta squared part, divided by m r cubed. So if you take the derivative of this with respect to r, you're going to get a 2r, the 2's cancel. It's in a denominator, so of course it's negatives, so you have everything in place. So there's the derivative of the first term. The second term, now I have a 1 over r in the denominator, so that becomes plus z then e squared over 4 pi epsilon 0, now r squared. Okay? Remember, all that's equal to 0. That means I can set these things equal to each other. All right, I have an r cubed, I have an r squared. Let's knock a couple of those out and solve for r. So if I'm going to flip all these upside down, where I have mr over n squared h bar squared is equal to 4 pi epsilon 0 over z e squared. All I did is invert both of those, setting equal to each other. Solving for r then, r becomes, bring this across, I have 4 pi epsilon 0 h bar squared, bring that over, divided by m(e) squared, and I'm going to have an n squared over z. How about the n squared and z across?
What's E?
Z
What's E? Tiny. What does E represent?
here,
Yeah, small E, not epsilon.
this one.
Yeah, what is
That is the electronic charge. It's a charge on the electron. And since the proton has exactly the same charge as the electron, see, we can just do it in multiples of how many protons. So this fits a hydrogen-like system. All right, now, these are nothing but a bunch of constants. I have epsilon 0 permittivity, I have Planck's constant, I have, this is the mass of the electron and the electronic charge. So if I then just go collect those numbers, here's what I did. I have here's now my 4 pi epsilon 0 h bar squared electronic charge me. Here they are defined. And when I produce those numbers, I carried out some digits. Now, with the new standards that they did in last June, I have to go back and refine that number of things. So they redefine these things. So there are the values, and I get a value of, guess what? 5.292 times 10 to the minus 11, the Bohr radius. So that is the predicted Bohr radius, and this is now written as a standard, or Bohr radius, m squared over z. And that's what we just saw in that general chemistry text. That's why I wanted to point it out to you. You didn't like that, Francis, why?
Is it A not the 4 pi epsilon 0?
It is all of this.
Okay.
All of that is AC. And when you produce those numbers, you get what's more predicted. And it turns out he was right, in a way. Okay, now, with that, we're almost done. Here is the energy. Let's calculate the energy of the electron in the hydrogen atom, okay? So I've now calculated the energy, the Hamiltonian, which is the energy, is the kinetic plus potential. All right, I'm going to do this. You'll see why I do this. This r squared here, I'm going to substitute one of those r's with this, and one of those r's with this. It's just so constants will cancel. You'll see why in a moment. All right. So the first term is going to be n squared h bar squared. That's my angular momentum squared according to Bohr. I have divided by 2m. Now, one of those r's, I'm going to do this. So it's going to be, if I flip that over, it's going to have an m(e) squared over 4 pi epsilon 0 h bar. So flip that upside down. Z over n squared. That's one of the r's. Flip this, pop that upside down.
Why is the h not squared in the denominator?
The square, thank you. It is. I'll just see if you're watching. And then the other one, I'm going to multiply by another r. It's going to be z over a0 n squared. Okay? And now that, remember this term is still 0. There's the angular momentum energy, kinetic energy. So now the attractive force, so it becomes minus z e squared 4 pi epsilon 0. Now I'm going to make another z over a0 n squared. Here's why I've broken it into two terms. If you'll notice, I have an n squared, one of those goes. My h bar squared goes away. I have the mass of the electron, which goes away. And so I end up as my total energy, I have a 4 times 2. So I have an e squared z squared over 8 pi epsilon 0 a0 n squared. So that's all these things put together, canceling out what I can do. Then the second term, I have a minus e squared z squared 4 pi epsilon 0 a naught n squared. So you see they're identical, except one's a 1/8 and one's a 1/4. So if I subtract them, I get my answer. I have an E squared, to collect the constants like again I did before, negative over 8 pi epsilon of 0, A0, Z squared over M squared. This term here, again, is a bunch of constants. And when I just collect all those constants together, put them all, here's the work that we've done, I get this value of 2.1784 times 10 to the minus 18 joules. And that, of course, is the Rydberg constant right here, 2.179 times 10 to the minus 18 joules. So that's how Bohr did it. And he produced that value. The question is, how good is it? Well, the other thing they tell you in general chemistry, by the way, this now becomes minus the Rydberg constant, Z squared over M squared. All right, now let's test it. Let's go look at the line spectra. Well, they told you in general chemistry correctly, they just didn't tell you why, but now you're about to find out, is that you have quantum numbers n equal 1. We'll see where quantum numbers come from, why do things get quantized. And then you have n equal 2, then you have a closer n equal 3, n equal 4, and that's all those numbers right there. So if I simply put the Rydberg constant, I'll set Z equal to 1 for a hydrogen atom. So this would be 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, and so forth, and so on. Well, that's what we do, of course, in atoms. We zap it with, a voltage, and we kick the electrons up, and then the electrons start coming back down, and that, of course, is what gives you your lines. And they're very, very fine. All right, so let's see. If I do that, here are just the energies themselves. So this is, I put a Z, so I put 1, so this is hydrogen. If you wanted to do helium, you can, whatever, to put a 2 in there. So here's the 1, 2, the 1, 3, the 1, 4, there's the 1, 1, those are any particular numbers. Well, we want the difference between them, because the difference between the electron going from here to here is what's given off as radiation. So I produced that, and there is then a line spectrum computed from the Bohr radii. Well, these are now given in units of angstroms. Notice they're all out of the visible range. These are all the transitions. The line way over to the right is the 2 to 1 transition. The next going in is the 3 to 2, and then the 4 to 3, and the 5 to 4, and so forth and so on. Okay? And you see they do indeed get closer together. Well, here is what I compute. Here's a Bohr model. 1215.023 angstroms. Here's what's measured if you go into the laboratory. 1215.67. Pretty close. The 1 to 3 is 1025.18. Literature is 1025.73. And the 1 to 4 is 972.02 and 972.54. They are just a touch off. And here's the reason why. In our model, we had this fixed proton, so there is the mass of the proton, and here we have an electron, so this involves the mass of the electron. In solving this, what we essentially did was to nail the proton in place, and had considered only the mass of the electron. However, if we go back, and instead of using the mass of the electron, use the reduced mass between them, because they're moving very, very, very slightly relative to each other. So if I replace ME with mu, or ME, MP, or the mass of the electron plus the mass of the proton, make that slight correction, look at what happens. So I've replaced it, and I do make the point, let's see, down in here, experimentally the Rydberg constant is 109.678 reciprocal centimeters. The value we're calculating here is 109.737. However, if I change the mass of the electron to the reduced mass, I then produce a value of 109.677.6, essentially the right answer. So let me recompute my spectra. So now the 2 to 1 calculated is 1215.68, literature 1215.67. 1025.73, 1025.73, spot on. 972.55, 972.54. Okay? You got it right. What he did not know, by the way, is that the electrons in their orbits, we'll see this later, They're doing two things. They're moving in a circle. Any charged particle that moves in a circle generates a magnetic field. It's also, and this was completely lost until much, much, much later, it is what we call, in big time, giant quotation marks, spin. It's not. It's something akin to it. It's not spinning. We have no clue about what it is. You'll see why later. However, a spinning particle also generates a magnetic field. So you have orbit magnetic field, you have spin magnetic field, they're interacting with each other, and that causes those lines to be very, very slightly split, called hyperfine splitting. And that is what's accounting for probably these like 0.68, 0.67. And part of what you're going to do in problem number 3 is kind of look at the relativistic effects, see how close that velocity gets to the speed of light. It's going to be kind of an amazing thing. So we have relativistic effects going on down there. We had the splitting due to magnetic fields forming, interaction between orbit and spin. So we had little very, very fine-tuned things that contribute to why these are just slightly different.
Why is the relativistic effects important here? Why do we need to know its relativity to the...
This is particular, and when you finally get down to francium, you'll see why. Because francium, the inner electron in francium is moving about 2/3 that at the speed of light. When that happens, a number of things happen. The particle gains weight, gains mass, it's heavier. It loses time, it slows. It shrinks in the direction of motion. So these are all relativistic effects that we have to account for. So when we're getting closer and closer to the speed of light, then these relativistic. So for electrons of lithium, minor. Not much at all.
Mass accounts for relativity effects.
Mm-hmm. And that's why it's so hard to computationally work with heavy metals. Because they have so many protons, they're driving the electrons so close, they're speeding up to enormous velocities. So then we have to account for all those things. It's an amazing phenomenon, okay? All right, then I alluded to that we had all these experiments that were failing and led us to Planck's constant. I just want to list a couple of them. One is called black body radiation. You can know this if you've ever seen a hot coil on a stove. You don't have to be in the room to know the stove is on. And you don't have to be in the room to know that the stove is either warm or hot or very hot, because we use the term white hot. We know that as a black body then begins to heat up, it begins to emit radiation, starts in the infrared region, finally grows, turns to the more blue side, and so forth. If you plot the intensity versus wavelength of a black body radiation at temperatures from 3,500 Kelvin to 5,500 Kelvin, you see the maximum, there's a shift as it goes in more to the blue side. It goes to a lower wavelength. Okay, well, classical physicists wanted to be able to reproduce that. So the first one that came up is one is known as the wide displacement distribution, and that one looked like this. So that was just a disaster. You could not figure out why. This, by the way, where this over here, this fits very nicely, but when it gets into here, it blows up rather than coming back down, and that was called the ultraviolet catastrophe. That's what that was termed down there. So, in comes Max Planck, and for the first time, he suggested that the vibrations of particles in that material can only have certain vibrations. They can only vibrate a certain way, aka being quantized. So he said these are going to have, and he's then leading off from Einstein, who's thinking about the light and matter type of thing. In fitting all this, he produced another expression and did a curve fit and produced the Planck's constant. When he did that, about 1900, he produced a slightly different expression, but over on the right is the graphic I just showed you, that's just a JPEG. The one over on the left is the Planck displacement law. So these are real numbers. I just calculated them in here from this expression right here. You see it matching beautifully. Here's the wide displacement law. So it comes as nice out here, but it kind of blows up. The rest of it fits nicely. All right, now we got to know why. Why is all this stuff happening? Going in a little further, if we go down to a photoelectric effect, this really caused a little bit of a problem. The photoelectric effect is one where you hit a metal with light and the electrons get ejected. So here's the classical question. I want faster electrons. What do I do to the light? The classical answer is turn the light brightness up. give me a brighter light. I'll give you faster electrons. That didn't happen. What happened is that I got more electrons traveling at the same velocity. So I turn the light up, it just generates more current. What did change is if I change the color of the light or the frequency. If I change the frequency of the light, then the electrons accelerate. Well, light, Einstein, Max Planck, Einstein put together what you call the stopping potential. Stopping potential, what you do is if you're ejecting electrons from a surface. So you got a metal surface, you got light coming in, the electrons are ejected. What you do is put a plate out here that has a voltage to it. And you turn up the voltage until the electrons stop hitting the plate. That means it's called a stopping potential. What voltage do I need to stop the electrons from just striking the plate? Well, that is a kinetic energy for the electrons, and there's the electronic charge, that's the voltage. Einstein set it equal to H frequency, owing to the light, plus a constant, or minus a constant. In fitting that, he reorganized that, and here's some data, and he found out that his straight line equation was indeed a straight line. And the slope of that line is Planck's constant divided by the electron charge. So this is happening, it's coming into play. Again, they're not sure exactly why. Finally, there is one that I show this because there's this movie out there. It is the stupidest movie of all time. It's really dumb. It's one of those new age, new wave garbage movies. They posit all this stuff. This guy is an anesthesiologist. He thinks quantum neurons are happening in the brain. He tries to prove it, which is utter nonsense. However, even in a documentary, which is I question, they even have some people in the movie that are channeling an ancient warrior or something. It's just dumb. You want to see it? It's like a feet in the air laughing type of movie. But anyway, it's called What the Bleep Do You Think? There's a name of the movie called Down the Rabbit Hole. Anyway. Even within movies like that, there is somewhat of a degree of precision and accuracy. One of the most interesting experiments in the early 1920s was that of a double slit experiment involving electrons. And so I have, really embarrassed about this, it's a cartoon from the movie that I've captured and put on, and it essentially describes the experiment and what happens within it. And so I'm going to show it to you as my everlasting shame. This is on the website. I always keep this up here. So there's my little cartoon character.
Here we are. I'm going to be a whole quantum weirdness. The infamous double slit experiment. See our partner. Or little balls of matter. Just a marble at the screen. We see a pattern on the back wall where they went through the slit and hit.
So you shoot a gun, you shoot bullets, you get a pattern in the detector. Awesome sound.
The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add this...
Well, Duke, doggy Duke. All right, here we go. I'm just going to describe the thing. All right. He's saying, all right, you have a panel, you fire bullets in a panel. Some of the bullets, some of the particles, some of the BBs, whatever you want to call them, go through the slit and make a very straight line pattern. If you put a double slit in play, you shoot those marbles, you're going to get two straight line patterns. However, all of you have seen a double slit experiment in a wave. If you do this with a wave pattern, then you have this double slit within here, the wave forms these concentric circles of high and low amplitude, and where they line up, and you can do this just by trigonometry, you find out you get a pattern on a detector that looks like this. Okay? Two things. One, ping pong balls, or you're shooting pebbles, or shooting, BBs, or whatever you hit. The detector strikes, or it detects events. Hit, hit, hit. You do the same thing when you look at radioactive detection. That's what a Geiger counter is doing. Every time you hear a little blip on a Geiger counter, it's an event. If you do wave forms, we have a wave gun out here, generator like this, like the white bars, then you're going to get this diffraction pattern in here that occurs that builds up all together. Now, this is the interesting part. We'll have another gun that will be an electron gun. Okay? Now I'm going to shoot electrons. When the electrons are shot, two things happen. The detector picks up events. Strike, 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 strike. But it builds up a diffraction pattern. So even though there are individual particles striking the detector, there's interference going on. All right, well, that then leads to that generates more questions than it actually answers at that point, because what are the electrons doing? So they decided a couple of different things. First, slow down the electrons where you're shooting one at a time. So electron, blip, electron, blip. So if two electrons are going through these slits, they're not interfering with each other or bouncing off each other or whatever they think might be going on down there. So one electron at a time will go through. Well, one electron at a time is the detector one at a time, and over time it builds up this exact pattern. So that leads to then this possibility. The electron is going through both slits at the same time. You know how that can happen, but that's apparently what's happening, because we're generating interference patterns even though we're only shooting one electron at a time. So they do this. They put in our double slit a detector. Put a detector in place, a little light flash or something goes through. Some little thing happens when the electron goes through this slit, so we know which slit it's going through. As soon as they put that detector in place, you get this. So the diffraction pattern disappears merely by putting a detector and trying to make a measurement on the system. This ultimately leads to what we're going to call the Heisenberg uncertainty principle. But the fact is that in a quantum system, and this goes even further, by the way, they're now arguing that you can alter quantum systems by thinking about them. And that's how far it's gone into evolutionary development of the quantum mechanics. But if you try to make a measurement, it goes through it. If you take this detector away, you get the diffraction pattern back. The mathematics says this. He says there are, at least for this simple system, there are four possible outcomes. The electron goes through neither slit. The electron goes through both slits. It goes through slit one or it goes through slit two. When you allow mathematically the quantum system to have all those probabilities, that's why we started the whole system, we're talking about probabilities and distributions. If you allow those probabilities to take place, you get exactly the right answers. But as soon as you try to make a measurement on it, it collapses into a particular given type of state. So this is called the principle of superposition that occurs within waves that come into play. And it was a real science experiment that actually had done that. So in leading to that, going back, just a brief introduction to here, we now have to throw up our hands and say, the universe is no longer governed by classical mechanics and Newton's laws. The universe is now governed by a new physics, and we have to find out what that physics is. Combinations. Einstein, light is a particle. This electron going through slits, particle is a wave. So they're beginning to merge, which the term is used as wave-particle duality. Particles and things and light can exhibit wave-like properties sometimes and particle-like properties sometimes. All right, well then the first one to kind of lead into this, again, this is bootstrapping, it's all this stuff is happening at the same time. Let's see if I have this photo. Maybe I can show you. But one of my favorite photos of all time. Louis de Broglie, little French guy with a mustache, he decided he needed to associate mass and a velocity, or momentum, a bit of matter, to a wave. and everything seemed to come to the same conclusion. He said that the momentum of the particle, which is of course the mass times the velocity, is Planck's constant divided by the wavelength of what that matter particle might be. Planck's constant is about 6.626, now it's known exactly, 10 to the minus 34th joule seconds. The magnitude of that number explains why we've never seen these effects before. If Planck's constant was 6.6, we would see quantum effects all the time. You'd throw a baseball and it would disappear and suddenly appear somewhere. Things would tunnel through walls. To illustrate this, I gathered this number and I said, okay, what would be then this quantum wavelength of different things? So first I took an electron traveling at 10 to the 5th meters per second, but kind of pretty standard for an electron. There's zippy little things. There's the mass of the electron, there's Planck's constant. If I used a de Broglie relation where I have mass times velocity being the momentum calculated, then it gives me a wavelength of about 7.3, 7.274 nanometers. That's measurable. You can see that. We have plenty of instruments that can measure down to that particular degree. But what if I did that to a 1 gram BB? Well, a BB traveling at 300 feet per second, velocity, I took about a 1 gram on this. We have velocity, we have a momentum, and that gives me a wavelength of about 7 times 10 to the minus 24th nanometers. So that is not measurable. We haven't got instruments that will do that. So it wasn't until we were able to get instruments that can measure down very, very finely that all these things began to appear. And these vibrations that seem to be happening in black body radiations and the vibrations in metals that lead to the ejection of electrons are quantized. We just didn't know why or where. So we developed a new physics. We will take off with this next time, but we begin with what Schrodinger. There's an old story that he actually stayed home from a skiing vacation in graduate school to find this. But he said, well, you know, all right, I would give up. I'm going to throw up my hands and say, matter is in wave. Well, what does the equation of a wave look like? Well, we've known that for thousands of years. The equation for a wave, it could be a vibrating string, it could be a water wave, it could be a sound wave, they all look the same. The differential equation looks like this. That's the equation of a string. So we can calculate the vibrations of a guitar using that very easily enough, okay? So what Schrodinger did is said, okay, I need to turn this into something that represents matter, okay? So that's what we'll do next time is I'm gonna give you just kind of a very simplistic argument, but it's gonna lead to what kind of mathematics we need to actually use and how we're going to be able to use them in there. Just as a side note on this, I'll reiterate this next time. This is a capital letter size indicated by the upper and lower horizontal bars. Whenever I write that, I'll just pick one dimension. This is a function of both space and time. So not only is this wave spatially distributed in space or whatever it might be, it's also oscillating in space. What we normally do is we say this in capital letters is equal to a lowercase psi multiplied by another function that is of time only, so x. So we break this up into a spatial part and an oscillating part, okay? Sometimes we can do that, sometimes we can't. I'll explain why and how we can do that. So whenever I see a lowercase psi, presume it's spatial only. If I have a 2GT, or see, you'll see what the form of that looks like next time. This is the time. The overall wave function that describes our matter is going to be these two multiplied together. That's going to be very important. Wave functions, when we put them together, like for example, I'm going to have a molecule that translates, vibrates, and rotates. So we're going to have a wave function for each of those motions. How do we get the wave function for the overall molecule? You multiply them all together. And then I want to see what does it do in time. I'll multiply it. So all wave functions will multiply. Energies will add. Two distinctions that we're hanging in those. So we'll launch next time with the classical wave equation. We'll put one of these in place, reiterate it, and see what Erwin Schrodinger stayed home from skiing vacation to garner. That will be the starting point of the most powerful equation in the universe. So we'll take that next time. Sorry about the video. Anyways.